All right, today we're going to take a look at section 4.3 and then 4.4, and then we're done with chapter 4, which means there's a test coming up. There's a test. It's actually great timing. This is great. The test is next Thursday, right before spring break. And why is that such great timing?
So we're not in the middle of chapter.
We're not in the middle of chapter, but there's something about it that makes it really great. There's no homework over spring break. You got it. Okay, so that's good news. No homework over spring break. So we will be doing a review in class on Tuesday. No homework for this class. Yes, you're right. I can only control one class at a time. So, well, one of your classes at a time. So yeah, we're going to have our test next Thursday. So today we're going to be finishing up chapter 4. 4.3 is arithmetic in the Hindu-Arabic numeration system. And in order to take a look at some of the things that we're going to do, we're going to need to talk about expanded form. We've talked about expanded form a little bit already. We've just done it for Babylonians and Mayans. We're going to look at expanded form for us to start with. So this is a form in which the value of the digit of each position is made clear. So instead of thinking of 942 in the form all compact like that, we think of it as 9 hundreds, 4 tens, and 2 ones. And we have a couple other ways we can write it notationally. This is 9 times 100, 4 times 10, and 2 times 1. Or, and what's actually a little bit more helpful for us to remember, is that all of those 10, 101, all of those are powers of 10 because we're in base 10. So I can rewrite the 100 as 10 squared, the 4 as 10 to the 1, and the 1 is actually 10 to the 0. Quick way to remember what power of 10 you're working with is that the power on the 10 is the same number of zeros in the number. The number 100 is 10 squared. The number 100 has 2 zeros. You see that? Just a quick way to keep that in mind. So what we're going to do is we're going to take a number that's written in standard form, like 942, and we're going to write it in expanded form. And then we're going to take a number that's written in expanded form, and we're going to write it back in standard form. A lot of going back and forth today in the things we're working with. So our number is 12,398. I'm going to do a sort of an intermediate step in doing this, just because I think it makes it a little bit more obvious what's happening. The 1 is in the 10,000s place. This is 1 times 10,000. The 2 is in the 1,000s place. 3 is in the hundreds place. 9 in the tens place. And the 8 is in the ones place. Everybody good with that? Okay. And then we're going to make each of those numbers that are base 10 numbers powers of 10 instead. So instead of writing 10,000 as 10,000, it's 10 to what power? 4. How do you know? There's 4 zeros. That's how. How about the number 1,000? 3 zeros. So 10 to the third. 100 is 10 squared. 10 is 10 to the 1. And 1 is 10 to the 0. There are 0 zeros in the number 1, so it is 10 to the 0. Now, going back the other direction is a little bit even simpler, more straightforward, as long as all the powers of 10 are present. So notice that they are on this. This is 10 to the 5th, 10 to the 4th, 10 to the 3rd, 10 squared, 10 to the 1st, and 10 to the 0. They're all there. So if they're all there, what that means is that I can actually write the number by just using the number that's being multiplied and writing those numbers down. So this is 5, 0, 3, 5, 6, 8. So 503,568. Is that good? Okay. I want to remind you of a property that you know about, but you don't really think about when you use it all the time. And we're going to sort of point out when we're using it as we do so. It's a distributive property. We're often presented with the distributive property sort of in the reverse of the way that this is presented. We usually see it written as what's on the right-hand side first, and somebody talks about sort of drawing arrows through or distributing the A over the parentheses. That's fine. It's an equality. You can write it in either order. But what we're going to be doing is using it like this, where we're going to take things that are both being multiplied by something, and we're going to be able to add them together and then multiply it by that same thing. And this works for all the numbers A, B, and C. We're going to be using it mostly for whole numbers, not mostly, only I think for whole numbers in our discussion today. So what we're going to do is we're going to be adding and subtracting in base 10, but in expanded form for our next examples. So we have the number 75 plus 34, and we're going to write them in that base 10 expanded form, which means I write 7 times 10, because it's 70, and 5 times 1, or you could write it as 10 to the 0 if you want. I guess our book probably is going to do it that way, so we'll write that way. So 10 to the 1 and 10 to the 0. Okay? Oops, that didn't end up moving with it. There we go. And then we're going to do the same thing with the number 34. So I have 3 times 10 to the 1 plus 4 times 10 to the 0. Okay, pretty good so far. Just breaking it apart, writing it down more explicitly, really. We can actually add from right to left or left to right. It doesn't make any difference. So since it doesn't make any difference, I'm going to go the way we read, from left to right. And so we're going to add down. Because 7 and 3 are both multiplied by 10 to the first, I can add the 7 and the 3 together. That's the distributive property. That's what allows me to do that. And you do it all the time, just sort of because it's natural to do so, right? They're both in the place of 10. So think about what happens when you add money together, right? If this were $75 and $35, you'd have no trouble saying that I have got 7 and 3. There's 7 tens and 3 tens. That's 110, or 10 tens. It's $100. Okay, so there are 10 to the 1s here. And then I have 9 10 to the 0s. Now the problem is that 10 times 10 to the 1 is a 2-digit number times 10 to the 1. So we would break this apart. This would be 1 and 0. I'm breaking the 1 apart, or the 1 and the 0 apart here. And this has to go up a place value. So this is 1 times 10 squared plus 0 times 10 to the 1. And then I still have my 9 times 10 to the 0. And then the numbers in front of the powers of 10 form my standard numeral 109. So you might be asking yourself, well, how's my math lab going to make sure that I really do this in expanded form? The answer is that they're going to actually have you put it in the columns times the things that it's times. Like it's going to look just like this, and you're going to fill in the numbers. So that is what it's going to look like, is just like this, okay? Not multiple choice or something like that, but it'll look just like this if I remember right. All right, so subtraction, very similar. It's got a little bit of a nuance to it that we'll have to pay attention to, but it starts out the same way. I write 7 times 10 to the 1 plus 4 times 10 to the 0. I'm subtracting 4 times 10 to the 1 minus 8 times 10 to the 0. So the first nuance is, notice I wrote subtraction here, right? I know the number is 48, and the 4 and the 8, they're added, but I'm subtracting them from what's above. So I'm writing it as subtraction. Or you can think of it as distributing the negative through. That's fine too. Now there's a problem with this. The problem is that while I can do 7 minus 4 in the tens column, I can't take 4 and take away 8, correct? So what we do in our standard algorithm is that we do something called borrowing or regrouping. And we do the same thing here. We take the number 7 and we borrow one of the tens. So one of the tens comes over and it joins the other 4 ones. So now I have 10 ones being converted, right? Think about like making change. You took a $10 bill and you turned it into 10 $1 bills. So now you have 10 and the 4 that were originally there, 14 $1 bills. So I'm going to rewrite this step. This would actually look like 6 times 10 to the 1 now, plus 14 times 10 to the 0. I'd be subtracting 4 times 10 to the 1, and subtracting 8 times 10 to the 0. Now, as long as there's enough on the top value to subtract off what's the bottom value, we can move again from left to right. So 6 minus 4 is 2. So this is 10 to the 1. And then 14 minus 8 is 6 times 10 to the 0. And our standard numeral then is the number 26. Okay, everybody good? All right, one of the oldest forms of speed calculation was an object called an abacus. An abacus is a physical object, okay? So these are drawing representations of a physical object, but it is a physical object. Like I could bring in to class an actual abacus and we could see that it has these rods going on and these beads in these locations and so forth. There are 5 beads along every rod. So my rods are my vertical lines that are drawn here. There's 1 bead above the rod and 4 beads below. Okay? Always. And the beads don't come off. So you can't just not write down the beads. Like they're on it's a physical object. Okay? So as we're taking a look at this abacus, if the beads are moved toward the middle, my math lab tends to have a color different than if they're pushed away from the middle. That wouldn't happen on a real abacus. They just all stay the same color of what they were to begin with. But they're trying to help you with the visualizing. So the numbers that are pushed toward the middle are the beads right now that show up as black beads. And the ones that are pushed away are showing up as blue. So if they're pushed toward the middle, they're active, they have value. If they're pushed away, it's almost like you've removed them from the abacus, but you can't. They're just pushed away to indicate that they're not being used. The beads on the top part of the rod are worth 5, right? Like a $5 bill, 5. The beads that are on the bottom part of the rod are each worth 1. And then these rods are our powers of 10, with the smallest on the right moving towards the largest on the left. So if we were to look at this abacus that's drawn here for us, this first rod, the 10 to the 4th rod, has 3 beads from the bottom that are pushed up toward the middle horizontal rod. So this is the number 3. The second one has 1 bead pushed up toward the middle rod. So this is the number 1. But on the 3rd rod, there's actually a bead from the top that's pushed down. It's worth 5. And there's 2 beads from the bottom that are pushed up. They're each worth 1. So that's a total of 7, right? What happens on the 4th rod? There's no beads pushed toward the middle. What would that mean? It's 0. We can have a 0. And on the last one, I have 1 bead pushed from the top down and 1 bead pushed from the bottom up. What's that one? 6. 5 from the top, 1 from the bottom. I have 6. So this abacus represents the number 31,706. Is that okay? It's a visual picture of a number. So what we're going to do is we're going to take a visual picture of a number, and we're going to write it down, just like we just did that example. And then we're going to do the opposite, where we're going to draw the picture. So take a moment to write down or to draw this abacus, because it's not in your notes, I don't think, right? No. Draw this abacus, and then it doesn't matter what color the beads are, just ignore the coloring, just shade them in with your pen or pencil, whatever you're writing with. Okay, so let's start counting. On the first rod, What number is represented by those beads? We'll start on the left. We're always going to move from left to right. It's a 1. There's only one bead that's pushed toward the middle. They've turned it to black, right? And it's from below. So it's the number 1. How about the second rod? Down 0. There's no beads that are pushed toward the middle at all. Third rod? 2. And 6. Okay, remember, beads that are pushed from the top down are worth 5. Beads pushed from the bottom up are worth 1. So this is the number 10,256. All right, now we're going to actually sketch an abacus the way that they would be drawn. So draw your abacus so that it has all the pieces there. We're going to draw in, whoops, still didn't get it right. Oh my word. It's better. 5 vertical bars that are our abacus value holders. 3, 4, and 5, and 1 through the middle. Every rod has to have 5 beads. 1 above, 4 below. We can't just leave them off. They have to be there somewhere. So the first number is the number 7. How do I get a 7 on an abacus? 1 above. 1 above, 2 below. Yeah, and then there's 2 more below down here that we have to put on there. Try to change the size of my beads. How about the number 0? How do I get the number 0? Push as far away as you can. So I've got 1 at the top and I've got 4 at the bottom. How do I get the number 1? 1 pushed up from the bottom. So I still have 3 at the bottom underneath it, and I have 1 at the very top. How do we get a 6? Yep, 1 on top and 1 on bottom. So I've got the bead that's on the top present, and I need 3 more beads on the bottom. Last one is 3. How do I get a 3? 3 from the bottom. So I need 1 more on the bottom, and I need 1 more on the top pushed away. And this would be the abacus that I have that would represent the number 70,163. Excuse the fact that my beads all look funny. All right, is that all right? Okay, there's one more thing that we're going to take a look at in this section. What we're going to look at is something called lattice multiplication or lattice method for products. What this is it's an alternate way to multiply 2 or 3 or 4, whatever digit numbers. That's what it really is. So let's just talk through what you do. You create rows and columns for your digits. You divide the boxes along the diagonal. You compute the single digit products with the top or the tens digit in the upper left corner and the ones digit in the bottom right corner. And then you add along the diagonals from right to left. So a couple of thoughts about this as a general statement. For those of you who are in education, this is taught in schools now. Not in every curriculum, obviously, but in enough curriculums that we definitely discuss it in our education courses, okay? All of you who are going to be parents, which is probably most of you in the room, will probably have some child in your home coming home with something like this at some point. It'd be nice that you've seen it. So that's good. Some of you are shaking your head and going, no way I'm having kids. I've got one in my house that's saying that. There's no way. Okay, that's fine. Maybe you have a niece or nephew. How's that? All right. This method has been around for a little while. So my daughter, who is a sophomore in college, you guys, some of you are in that freshman, sophomore year in college, you're very close to her age. When she was in third grade, and she is typically very adept at mathematics, multiplying with standard multiplication was difficult for her. I don't know exactly why that happened to her, but she just was struggling. And so I brought home tools that I use to teach, my education majors, a couple of them, and I showed her a couple of different methods, and this was the one that she just sort of grabbed onto, and it resonated with her, and it really made a lot of sense. Now, did she multiply like this forever? No. She figured out the standard multiplication, and it eventually was just fine to do that for her. But for a while, this was a really good bridging place for her to be so that she could still do what needed to be done, but in a different way. So let me show you how this works, because writing down the steps is harder than actually doing the process, okay? So we're going to do the number 912 times 483. And the first thing we're going to recognize is this is a 3-digit by 3-digit number. Yes? So we need to do a box that has 9 boxes inside of it. So 3 columns and 3 rows. Mine are a little bit lopsided, but that's okay. And we're going to split the boxes along the diagonal. So this is my diagonal. Like that. Everybody good? All right. Because these are both 3-digit numbers, it doesn't really matter what I put along the top and along the side. If it were a 2-digit by a 3-digit number, you just make sure you put them in the right place for the way you've drawn your box. But I'm just going to go in order. So this is 9, 1, 2 along the top, and then 4, 8, and 3 along the side. And they do have to go along the top and the right. They can't go on the left. We're going to be doing something on the left-hand side, okay? Alrighty. So one of the things that makes multiplication challenging when you actually are doing multi-digit multiplication, like a 3-digit number times a 3-digit number, is that in the middle of multiplying, you add something together. You know what I'm talking about? You multiply 2 numbers together and you get like 24, and you write the 4 down and you carry the 2 to the next column. Yeah? And then you multiply it, then you add the 2 that got carried. So in the middle of multiplying, you add. The other thing that makes multiplication a little bit complicated in the standard multiplication is that we put these 0 placeholders in that feel a little mysterious, to be honest. They just sort of show up. So we don't have anything happening like that with this method, so let me show you how it works. Each of the boxes, these diagonal boxes below, are the product of the column that they're on and the row that they're on. So if we go to the row that we're on, sort of here. So if you go to the top left-hand corner, you've got a 9. And if you go over to the far right-hand top column, you've got a 4, right? 9 and a 4. What's 9 times 4? 36. And we write 36 in just like this, 3, 6. And we're going to do this for all of our boxes. The next one is 1 times 4. That's 4. Single-digit number just goes in the bottom right-hand corner. And then 2 times 4 is 8. 9 times 8 is 72. 7 in the top, 2 in the bottom. Whoops. 1 times 8 is 8, and then 2 times 8 is 16. 9 times 3? 27. 1 times 3 is 3, and 2 times 3 is 6. Okay, so we isolated every bit of multiplication. We did it all at the beginning, right? So that's good news. The next thing we do is we extend the diagonals of our box. So all these diagonals get extended down like this. And now it matters where we do our addition. We're going to start in the bottom right-hand corner with addition. Everything that's outside of the box is nothing that we're adding together. So mark them out, erase them at this point, whatever it takes for you to not get distracted. The 9, 1, 2 on the top and the 4, 8, 3 on the bottom are not involved in my next step. We're done with them. Everything in the box gets added. So the bottom right-hand corner, there's just a 6, so I write the 6 down. But the next diagonal is 6 and 3, right here. And I add 6 and 3 together to get 9. So I'm going to write a 9 here. The next column has quite a bit added. It has an 8, a 1, an 8, and a 7. It is 24, okay? You can add it quickly in your head. Great. You want to grab your calculator to confirm your addition. That's great. Whatever it takes. It's 24. So you write the 4 down, and you do end up carrying the 2 over. So this number is a carried number. Okay, 24. Now we're going to add our next diagonal, 2, 4, 2, and 2. What's that one? 10. So we write our 0 down and we carry the 1 over. And then this diagonal is 1, 6, and 7, which is 14. Write down 4, carry my 1 over. And I have 1 and 3, which is 4. Whoops. My answer then is right here. The answer to this multiplication problem is 440,496. Okay. I don't remember who came up with it. I'm not sure. All right, so here's what you need to know is that what's happening when you move these diagonals is you're replacing them into the right column that they're supposed to be in, right? Like that's what happens in our standard algorithm too, is that we're putting, the tens number into the tens column, the hundreds number into the hundreds column. So that's what's happening. But from a very practical sense of what you're doing inside of like your technology environment for your homework, you should check everything you just did, right? So I saw Caleb already did it. He checked to make sure that we got the right answer. You've got 912 times 483. This number at the bottom should be what your calculator says it is, right? It should match. Now, what does this look like in my math lab? Well, it looks like them giving you the box, and you have to fill in all the numbers in the box. And you have to tell them the answer at the end. So again, you've got a calculator, you've got scratch paper. Check and make sure that you're not accidentally writing down, that 9 times 8 is 56 or something like that. Make sure that you're doing the arithmetic pieces right so that you're not missing any points on it, because you can check this one really easily.